To the Mathematics of Cryptography conference at UC Irvine. And I'm glad to see that all of you came. So I want to thank the Alfred P. Sloan Foundation for generous support. And I want to thank all of you for coming. And this should be a fun conference, and it's going to be very laid back. We're going to be in California time, and we're going to maybe change the order of talks and things like that, and things will take longer. So feel free to ask lots and lots of questions. So we want to have a discussion here. We don't just want to have people be presenting talks and everybody falling asleep. We want everybody to be paying attention. We want you to be solving problems. We want the speakers to give open questions that people can solve, and we want it to be a productive and a fun conference. Please sign the registration form, even if you emailed me in advance that you're registered. We need a list of who actually showed up. So if you're only here for a day or only here for a few minutes, please sign the registration form. There's also the boat trip sign up. Maybe I'll talk about that at the next break, and we'll talk about tomorrow and tonight and things like that. But maybe I'll turn this over to Daniele. So I'm happy to introduce the first speaker, Daniele Micciancio, and he's going to be talking about lattice cryptography, introduction, and open problems. Yes.
Thank you for the introduction. So yeah, I'll be giving an introductory talk, and I've done this before, so I'll try to give a different introductory talk. The talk today will be, it's based in part on a talk I gave at the Simons Institute about 2 months ago on the history of lattice-based cryptography. For the few of you that were already there, the first half of it, yeah, it's something that you've already seen. Probably the most interesting part of that was the discussion and questions that came up, so the questions may also be different. And so let's get started. That's not what I wanted to do. Yeah. Yes. Well. Okay, this worked. For some reason, yeah, the screen here turned black, but yeah, that better than the other way around. Okay. So, well, as an introductory talk, I have to start with the definition of lattice. Hopefully, you will not get to see this for every single talk in the whole week. It will be only one. So, a lattice is a discrete set of points regularly arranged in Euclidean space. The simplest example of lattice is Zn, the set of vectors with integer coordinates. And more generally, an arbitrary lattice can be described as the result of applying a linear transformation to Zn. So you have a set of vectors, B1 to Bn, linearly independent vectors, and you take all the integer linear combinations of these basis vectors, and that's the general definition of a lattice. Now, lattices have a long history in mathematics, the study of lattices. I've been studying and working on lattices primarily from the computational point of view. And there are two main events that marked the development of the use of lattices in computer science. One of them certainly is the development of the LLL, lattice reduction algorithm, that was key to developing many algorithmic applications. So that's an algorithm that can efficiently find approximate solutions to lattice problems. And it had a lot of applications in mathematics, optimization, and computer science. So in cryptography, it was used primarily for cryptanalysis. So as an algorithmic tool to crack cryptographic functions. And that was the main use of lattices till the mid-90s. When there was another breakthrough occurred, Aitai showed that lattice problems exhibit an interesting connection between their average case and worst case complexity. And this is the work that marked the beginning of the use of lattices in cryptography the way that they are used today. So there were cryptosystems closely related to lattices even before that, like the knapsack-based cryptosystem. Around at the same time, the N-true crypto system was also proposed in 1996 and published in 98. And I will talk more about that later. But for now, let's just focus on this result. And these are a few quotes from that paper. So what I argue in that paper is that in cryptography, you need hard problems. And based on our current state of knowledge, we don't know how to get problems which are guaranteed to be computationally hard and still useful for cryptography. Think of it, what if P is equal to MP? Something that we are still not able to disprove. So any hard problem that is used in cryptography has to rely on some kind of assumption, and we need to guess what could be a good hard problem to start from. And there are two ways that the cryptographers go about finding hard problems. One is try to tap into computational complexity, for example, in the theory of NP hardness. So NP hard problems are as hard as it gets when it comes to problems within NP, and there are many such problems. So you could try to use one of those problems. That was the idea behind the crypto systems based on the subset sum or knapsack problem. And the other possibility, which is the one that has been more fruitful and successful in cryptography, is to look at very questions from mathematics. Computational problems that have been studied by mathematicians for a long time and they are still unsolved. And factoring is the classical example of one such problem. However, unfortunately, in both cases, both in the case of NP hardness, in the case of, say, factoring, what is meant by difficult is difficult in the worst case. Now, if somebody comes to you and tells you, hey, I found an algorithm to efficiently factor numbers, what you expect is that the person discovered an algorithm that on input any number produces its factorization in an efficient manner. So difficult is the logical negation of this statement. And that means that for any efficient algorithm, there is some input for which the algorithm gives the wrong result, or for which the algorithm takes a lot of time. And clearly, that's not enough for cryptography. In cryptography, you need to find these hard instances. It's not enough to know that there is some hard instance that fails the algorithm. You need to find them. And these kind of worst-case hardness assumptions do not provide any guidance about how to find these hard instances. And it has been long realized that one way to generate such hard instances is to come up with a random distribution of problems and prove that any algorithm that can solve these problems with some positive probability, even if very small probability, can be used to solve the mathematical problem, the underlying mathematical problem in the worst case. And that's exactly what I did in that paper using lattice problems. And that's what attracted a lot of attention within the computer science and computational complexity community and set these lattice problems somehow apart from other problems that were being suggested for cryptography. Now, what I want to address now is a question that comes up many times. I heard this question being asked many, many times, both from computer scientists and mathematicians. And the question is, what is the difference between this and the number theoretic problem? It's still really not clear. For example, if we look at a standard, more conventional cryptography based on number theory, we have this classic problem, the discrete logarithm problem, where you are given a group, typically the set of integers modulo a prime, the multiplicative group of the set of integers modulo a prime. And so assume you have a generator G for this group, and you are given an input, which is G to the power I. And the discrete logarithm problem asks, given G and H and P, the description of the group, recover I. Recover the logarithm of H to the base G. And it is well known that this problem is random self-reducible. So you can show that if you can solve this problem on the average, even for very small probability epsilon, then you can solve it for any G and H. And so this is a standard proof in introduction to cryptography, and it's very simple. So assume you are given G and H, and you want to compute the logarithm of H to the base G for these specific values, for this G and this H. And but what you can do is only to solve this problem at random. You can solve it when G and H are random. You cannot solve it for this specific instance. Now you can proceed as follows. You can raise G and H to some random power. So you can raise G to the power A and H to the power AB for randomly chosen integers A and B. And these new values, G prime and H prime, are, if not uniformly random, they are very close to random. So depending on the invertibility of A and B, it may not be exactly a uniformly random distribution, but it will be very close, to the point that if you can solve this problem with probability epsilon, when G prime and H prime are chosen uniformly at random, then if you repeat this process 1 over epsilon times, then you expect that one of these attempts will succeed. And you will recover the discrete logarithm of G prime to the base H prime, which if you do the math is the number I times B. And you know B because you picked B at random, and you were trying to recover I. You didn't recover I. What you did was to recover this product, I times B, and you can recover I just dividing this result, J, by the non-integer B. So this gives a strong connection between the average case complexity and worst case complexity of the discrete logarithm problem, and that's why we think that this is a good problem to be used in cryptography. So what is the difference between these and lattice problems? Don't we already have a problem that is harder to solve on the average? And yes and no. So this proof shows that you can randomize G and H, so it provides a guidance about how to choose G and H. G and H should be chosen as random. That's a good way to choose them. However, it doesn't give any hint about how to choose the group G. And so all this proof is connecting different G and H, but always for the same group. Now, we can contrast this with lattices. In lattices, we still have not a single distribution, we have a sequence of distributions or a sequence of problems in increasing size. The complexity of lattice problems grows with the dimension n of the lattice. So the conjecture is that the complexity of solving lattice problems grows exponentially with this dimension n. And in the case of the discrete logarithm problem, the situation may look at first sight sort of similar. So we have discrete logarithm, this discrete logarithm problem in different groups. We can consider groups of growing size, and we can assume that the complexity of this problem grows exponentially in the description of the group. But the difference is that in the case of lattice, for every fixed n, we have this class of lattices, n-dimensional lattices. And what I showed is that you can solve it in the worst case for any choice of the lattice, if you can break a certain cryptographic function. In the case of the discrete log problem, for any n, for any group size, there are exponentially many primes, p. So there is not just a single, group. There are many of them. And this prime is typically chosen at random, so you still have an average case assumption. You're assuming that when the prime P is chosen at random, then with high probability, you get a group for which the discrete logarithm problem is hard. So the assumption is an assumption that depends on the distribution of P. And we do not know how to relate different P's and different Q's and make a connection between different values. And of course, you may expect that this problem is hard for any choice of P. No matter how you choose your P, then the problem is hard. And yeah, that's false, but then you can try to rule out the weak classes of P's and then get to a point where you can expect that, yeah, if you're choosing your group within satisfying certain conditions, which are based also on our current knowledge of algorithms to solve this problem, then you are on the safe side. I mean, if instead of choosing P at random, you were to choose it according to some other distribution, probably they wouldn't raise any objection in cryptography. But if you assume that, provided you rule out the weak cases, if you assume that, oh, they're all the same and they're all hard, I mean, that's an even stronger assumption than assuming that the problem is hard on the average. You're assuming it is hard for any value of P and Q, and you may even, at that point, you may even just fix the choice. For example, you can change the assumption by fixing, for every n, you could pick Pn to be the smallest prime, possibly satisfying certain conditions, so that is not a weak one, that is at least n bits in length. And so if you do that, then you get an assumption which is closer to what we have in lattices. For every n, we have this class of n-dimensional lattices, and the assumption is that the problem is hard. And for this specific choice of the prime, then you can still give a reduction between the average case and worst case complexity of the problem. But you will clearly, acknowledge that this assumption and fixing Pn this way is something that is certainly ad hoc, and it's even specific to the way we are writing the numbers. So if instead of writing the numbers in binary, you write them using decimal notation, then most likely you would want to replace that choice of P with Pn being the smallest prime that is bigger than 10 to the n rather than 2 to the n. So it's certainly a very ad hoc assumption. But there is more than that. In the case of lattices, when you consider lattices in bigger and bigger dimension, in a sense, you're dealing with the same problem, but with different size. You can always take a lower dimensional lattice B and then look at it as a higher dimensional lattice, just adding additional dummy coordinates that maybe contain some very big value. So it is irrelevant to finding short vectors in the lattice. So you can think of this sequence of problems, solving lattice problems in larger and larger dimension, as a single problem, but parameterized by the size of your input instance. So in some technical sense, we are dealing with a single problem, and we are looking at the complexity of solving this single problem for larger and larger instances. And in the case of discrete log, we don't know how to do anything like that. So we don't know. So assume that we fix. Yeah, so you can think of it as a single problem. So even if for every n, you can consider the set of solving lattice problems in n-dimensional lattices, and usually this dimension is considered as fixed. So the lattice problem that come up in lattice cryptography, more than a single problem, is a sequence of problems in larger and larger dimension. So in the case of lattices, you can still think of it as a single problem of larger and larger size. And it is the single problem in the sense that you can think of, say, lattices in dimension, say, 100. You can think of them as a subset of the lattices in dimension 1000 by embedding your lattices in dimension 100 into a bigger matrix. So you can think of these as small instances of that lattice problem. So if you want to find a short vector in this lattice, you can look for a short vector in this other lattice with this bigger basis matrix. Now, these coordinates are very big. So if you find a short vector in this lattice, sure, you are not going to use them. And what you are going to find is exactly a short vector in the original lower dimensional lattice. Yep. So, okay, so that was my point. While for the discrete log problem, we don't know how to do anything like that. If you take groups of larger and larger size, say integers modulo a prime that is n bits long, we don't know how to reduce the discrete log problem for primes that are n bits to primes that are n plus 1 bits or 2n bits. The problem changes, and I mean, I don't think it's true, but one could conjecture that, oh, maybe this discrete log problem is easy when the prime modulus has an even number of bits, and it is hard when the prime modulus is has an odd number of bits. I mean, that would be very, it's very unlikely that that's the case, but that's not something that we can disprove. So, I mean, who knows? So there is no, we don't have any formal way to show that the bigger the modulus, the better. So what we know about these problems, in the case of lattices, you can formally argue that if you increase the dimension, the problem gets harder and you get more security. In the case of the discrete log problem, well, based on the currently known algorithm, we know that if you increase the modulus size, the problem becomes harder to attack. So we think it is more secure. But there is no formal proof that that's the case. And who knows, maybe, yeah, it could be that somebody will find one day an algorithm showing that, oh, for certain size, yeah, discrete logarithm is easy, and you need to choose group sizes that satisfy certain constraints. So one more slide about this comparison between lattices and problems from number theory is that in the case of number theory, the hardness of this problem is tightly related to the representation of your group elements. Now, the ZP star, the multiplicative group of the integers modulo p, is isomorphic to the additive group of the integers modulo p minus 1. So, but if you represent your group using additive notation, then the problem is easy, and it's not hard. And now it's not about addition versus multiplication. In the case of elliptic curve groups, additive notation is commonly used, and they are both, I mean, it's a commutative group. But yeah, if you change the representation, then the complexity of the problem can change a lot. Now, that's true for any problem. You could come up with a different representation of lattices, where the description of a lattice is given by a pair, which is the basis of the lattice and the length of the shortest vector in the lattice. Okay, so, but in this case, we have a very natural representation, and you can also check that the representation is correct. In the case of lattices, it would be kind of not quite natural to add this additional information in the lattice description, and even if you add it, we don't have any way to check that this side information that is provided to you is correct or not. So also you can also choose other groups. Instead of working modulo prime, you could use, say, elliptic curve groups, or you could choose integers modulo product of two primes. So there are many other choices. And again, what we know about the complexity of this problem does not provide any guidance about the choice of the group. And just to illustrate this, consider this hypothetical scenario. So you have to choose between these two classes of groups, and assume, which is not true, that once you choose the group, we know how to choose these groups in a way that is guaranteed to be hard. And you have to choose whether you want to work modulo prime or modulo the product of two primes. And now I tell you that for one of these two choices, the problem is easy, is solvable in polynomial time. For the other one, it is hard. Okay? So which one would you choose? Is the question clear? So last time I gave this talk, Ron Rivest was in the audience, and of course he went for P times Q. Yeah, but that's I'm sure that yeah, Adi Shamir or Len Adelman would also pick P times Q. But that's a biased bet. So just think about security. You have no stakes in the choice of RSA primes, RSA mod groups, or working in a group modulo prime. So I tell you, one of them, I mean, I don't know that. Assume that, yeah, I made some breakthrough discovery in number theory, and I can tell you that, you know, for one of these two choices, there is a polynomial time algorithm. For the other one, there is not. It's hard. And just based on the information, which class of groups would you choose? So that intuitively, I mean, the typical choice is to work modulo prime. I mean, if you don't need it, why would you work modulo product of 2 primes? But technically, that's the wrong choice. And the reason is that by the Chinese remainder theorem, you can embed the ZP into the group ZPQ. And so if you can solve the discrete logarithm modulo P times Q, then you can also solve it modulo P. And the way you solve it modulo P is you're given your value modulo P, then you can pair it with a random value modulo Q, and you get a random value in PQ. You can take this discrete logarithm modulo PQ, and that gives you the result of the original problem. So if you can solve the discrete logarithm problem modulo PQ, modulo a prime product, then you can solve it for both of them. Then they are both easy. So if I tell you that one of them is easy and the other one of them is hard, the only possibility is that it is easy modulo a prime, but then it becomes hard modulo a product of 2 primes. And so giving a reduction in the opposite direction seems to require factoring, the ability to factor your modulus into the product P times Q. So it's not clear how to go in the other direction. So the choice of the group in these number theory based assumptions in cryptography can be quite tricky, and the theory and mathematical and theoretical study of algorithms doesn't provide much guidance about how to choose them. All our choices are based on the current state of the art in algorithms. We look at how hard it is to break one or the other one based on the current state of knowledge, and based on that we make our choices. Okay, so how all of this changed with Aitai's discovery? So he showed that there is a specific way to build the cryptographic functions that allows to prove that if you can break the function, then you can solve lattice problems in the worst case. So if there is any hardness at all in lattice problems, then that's a good way to choose your problem at random. And the problem is the following. The problem description is a matrix A modulo some integer Q, which may or may not be a prime. Think of Q as a small number. It's not a hard-to-factor number. It could be some number that is just a few hundred, is in the hundreds range, not 100 bits. So it's something that can be represented into a single computer machine-level word. So, and the input, so this matrix A describes a function. The input is a binary vector, or more generally, a short vector, and the function is just a matrix vector multiplication and modulo Q. And what Aitai proved is that if you can break this function, if you can invert this function on the average, even with very small probability epsilon, then you can solve approximately lattice problems in any n-dimensional lattice, when n is exactly the n that comes up in the choice of this, in the dimension of the matrix. And so this, Yes, I have it in a, it's a short integer solution problem. I think I have it spelled out in a later slide, and I had included here just to, for reference. And this SIVP, again, it will show up spelled out in a later slide, is the shortest, smallest independent vectors problem, which I'm going to define. The theorem says that if you can invert this function on the average, that is given A and given f of A, which is A times x modulo Q, recover x. and X is a, say, 0, 1 vector. Think of it as a subset of the columns of A, which adds up to that value. Now, if you can solve this problem on the average, when A is chosen at random, when X is chosen at random, and even if you can solve it with, say, 1% probability, that can be turned into an algorithm that solves lattice problems efficiently. I mean, one specific lattice problem. This is the problem that is being solved. I will talk more about it. So it solves this problem in the worst case. So given any lattice, possibly completely unrelated to this matrix A, other than the fact that the dimension of the lattice equals the number of rows in this matrix. So given any lattice in n dimension, you can find short vectors in this lattice. More specifically, you can find n linearly independent short vectors in that lattice, and I will define. I will make this more formal by defining the problem soon. Is it clear? Sorry? Oh, the accuracy of the approximation is that you can find an approximate solution to this problem within an approximation factor that is polynomial in the dimension n. And in High-Tie's theorem, this was a large polynomial. In fact, the polynomial would get worse and worse with the complexity of the algorithm, I believe. But then it was brought down, and the latest work, I think, is the one from my work with Oded Regev, where we show that the approximation factor is essentially linear in the dimension n. So you can approximate lattice problems within a factor n. And this is a very simple cryptographic primitive. It's just a one-way function, a function that is easy to compute but hard to invert. It doesn't give you public key encryption, but it is enough to build many other things. You can build collision-resistant hash functions. You can build cryptographic commitment schemes. You can build digital signatures of a certain kind. And the problem is clearly related to lattices. In the sense that, so think of the hashing. You want this function to be collision resistant. So for this value of parameters, when m, the input size is bigger than n log q, and log q is the output size. The output is given by n values modulo q. So for the range of parameters used by High-Tie, so this is a compression function that takes a longer input and produces a shorter bit string. So you can show that not only this function is hard to invert, it is also hard to find collisions to these functions. Different inputs which are mapped to the same output. And the problem of finding collisions can be easily formulated as a lattice problem. So consider the set of solutions to the homogeneous system, AZ equals 0, and finding a collision that is two strings, x and two inputs, x and y, which are binary vectors, such that AX is equal to AY modulo Q. Now you can take the difference between these two vectors, x minus y, call it z, and if you multiply it by A, you get that A times z is equal to 0. And z is a non-zero short vector because it is a vector with 0, 1, and minus 1 coordinates. And x and y are different inputs. So they are different, cannot be 0. It is not an all-zero vector. So finding collisions is clearly related to finding short vectors in this lattice. But there is a much deeper connection between this problem and lattice problems. Now, as long as all we say is this, we are saying that breaking this function is as hard as solving this lattice problem on the average. So this is not a worst-case lattice problem. We are considering a lattice that depends on the choice of the matrix A. And for every matrix A, there is a corresponding lattice, and breaking the function keyed by A correspond to finding short vectors in a lattice that is also described by the matrix A. Now, that's not the interesting part of the connection. I mean, it is interesting to the extent that we know that breaking this function is not harder than lattice problems, but it could also be much easier. So also, the identity function can be inverted, given an algorithm that finds collisions, that finds short vectors in the lattice A. And you just don't use that oracle at all, and you just invert your function. So what I showed is that you can also proceed in the other direction. You can start from an arbitrary lattice, and assuming you can find collisions, then you can find short vectors in this arbitrary, unrelated, n-dimensional lattice. And in order to describe this connection, I need to formally define the lattice problems that we could start from. So there are several standard problems on lattices. One is called the shortest vector problem, SVP, where we are given a lattice in n dimensions, typically, well, k dimensions here, typically described by a basis matrix. So here we have a two-dimensional example, B1 and B2. Now you can generate the lattice spanned by B1 and B2, and when you take all the integer combinations of B1 and B2, you can get lattice vectors which are much shorter than B1 or B2. And the question is to find such a short vector. For example, in this picture, the shortest vector is obtained by taking B1 5 times and subtracting B2 twice from it. And you can also think of it as putting a ball around the origin and then increasing the radius of this ball until it contains a non-zero vector. And the length of the shortest vector in a lattice is typically denoted with a symbol lambda 1. Now, in the approximate version of the problem, you don't ask to find a vector of length lambda 1, you ask to find a lattice vector of length at most gamma lambda 1, where gamma is some approximation factor. For example, for approximation factor 2, you take a ball which is twice as big, and any green point inside this picture is considered a valid solution to the SVP approximation problem with approximation factor gamma. Another problem is the inhomogeneous version of SVP, where you're given not only a lattice, you're also given a target point T. And again, you consider all the points spanned by B1 and B2, and you want to find the point that is closest to the target. And again, you can consider this problem in the approximate version, where you want to find something which is not you want to find a lattice point at a distance from T that is not much bigger than the optimal. Now, this is the closest vector problem, CVP, and together with SVP, these are the two most famous, classic algorithmic problems on lattices. Now, it turns out we don't know how to build the cryptographic functions based on these two problems. We often think of lattice cryptography as something that is based on these problems, but it turns out that we don't even know how to build one-way functions based on the assumptions that these problems are hard. And for cryptography, we need one more problem called the shortest independent vectors problem, where you are asked to find not only one short vector, you're asked to find n linearly independent vectors which are as short as possible. That is, take lambda n to be the radius of the smallest ball that contains n linearly independent vectors, and you want to find n vectors within that ball. Notice this problem is not harder than SVP. Solving this problem does not give you a solution to SVP, and the reason is that this radius lambda n can be arbitrarily larger than lambda 1. So as usual, you can also consider the exact or approximate version of the problem, but more than that, more interestingly, in the case of lambda 1, you can define this parameter lambda 1 as the distance between any two lattice points, that's the minimum distance of the lattice, or the radius of the smallest ball that contains a non-zero vector. Now, as soon as you have one vector in this ball, you actually have more than one vector. You have at least three vectors. You have the origin, the short vector, and also its negation. But all these points, they lie on a line. They are linearly dependent. And you can generalize this parameter, lambda 1, to, you can consider a larger radius such that all the points inside a ball of radius lambda 2 span a set with Euclidean, with dimension 2. And if you're in n-dimensional space, you can define a sequence of parameters, lambda 1, lambda 2, all the way up to lambda n, where lambda I is the radius of the smallest ball that contains I linearly independent vectors. In the case of Zn, all these values are the same. Lambda 1 is equal to lambda n, and they are all equal to 1. But in general, all you can say is that there is an increasing sequence, and you can easily build lattices where these numbers get larger and larger. So solving SIVP, the shortest independent vector problems, does not give a solution to SVP. Because you find n linearly independent vectors of length lambda n, which is potentially much larger than lambda 1. Now, this is the problem that underlies all modern lattice-based cryptography. And building cryptography out of SVP or CVP is one of the open problems in the area. Or maybe understand why we can build cryptography out of SIVP, but we cannot build cryptography out of SVP or CVP. Now, SVP and CVP can be used to attack lattice cryptography. So it's not that they have no place in cryptography, but we don't know how to build cryptographic functions which are as hard as solving those problems. Now, in order to connect this problem, SIVP, with Hightise function, we need to introduce one more parameter. I will not give a formal definition, which is based on Gaussian distributions on the dual lattice. I will just illustrate it with a picture. Now, consider starting from an arbitrary lattice lambda, and then blurring this lattice, adding some noise to it. And then you increase the amount of noise that you add to this lattice. You add more and more noise. And you can, at some point, you will cover the entire space. And when you cover the entire space, the radius of these spheres is called the covering radius of the lattice. Is how far from the lattice can you be in the worst case. And it is easy to prove that this covering radius is at most square root of n times lambda n. So this covering radius is related to this nth lambda n parameter. Now, you can go beyond that. You can even use larger noise. And notice here in the picture, you get different shades of red. I mean, so pale that it looks like almost white or pink. But the more spheres overlap, the darker it gets. And if you think of this as a process of picking a random lattice point and then adding a random error to it, this shade corresponds to the probability of ending up in one or another region of space. And if you increase the amount of noise, you will get that the color of this picture will get closer and closer to uniform. And you can define a parameter, this is called the smoothing parameter of the lattice, which is how much noise you need to add to a lattice in order to not only cover the entire space, but cover the entire space in a way that is close to uniform. So close to uniform that you cannot tell the difference between these different shades of red in the picture. And it is possible to prove that you don't need to go much beyond this bound. If you just multiply by a logarithmic factor, that's enough to get within negligible statistical distance from the uniform distribution. Now, uniform, here I'm using the term uniform as an informal way. There is no uniform distribution in Rn, but everything we are doing is periodic modulo the lattice. So formally, we are working in Rn modulo the lattice lambda, and you can show that the distribution is closer and closer to the uniform distribution over this compact set. And real numbers, in computer science and algorithms can be problematic at times, and because of precision issues. You don't really need to use real numbers. I will not get into the details, but you can essentially replace using techniques from work of Gentry, Peckert, and Vaikunthanathan, where this Rn is replaced by a very fine sublattice of lambda. You can take lambda and then divided by a factor q for a sufficiently large q, but not too large q, and then you can replace the real numbers with this fine grid. Now, what is this all good for? So I'm taking V to be a lattice point. Think of choosing it uniformly random. Technically, we are working modulo de lattice. And then you add to a uniformly random V, you add a random error, a noise vector R of length bounded by a little bit more than lambda n. So if you do that, then this sum V plus R, this noisy lattice point, modulo de lattice, will be almost uniformly distributed. And what is important here is that this distribution does not depend on the lattice. I mean, you get the uniform distribution, so the lattice somehow disappears. By adding noise to the lattice, you erase the fine discrete structure of the lattice, and you end up with Rn. And this is what can be. So I didn't use these techniques. This technique came up later to improve that proof, but to get the same result. Now you can prove the High-Ties theorem as follows. Now do this many times. Pick many random lattice points Vi, and for each lattice point, pick also a random noise vector Ri. And then compute the sum V plus R modulo de lattice. And the result is a vector which is statistically close to uniform. So you can uniform in Rn or uniform in this scaled down version of the lattice. So it's something that looks like a random matrix, the kind of matrix that is used in High-Ties function. So, and no matter which lattice lambda you start from, if you perform this process, you will end up with a matrix which is statistically close to a uniformly random matrix modulo Q. So it is a good target for a hypothetical cryptanalytic attack that can invert the function. So assume that we do have an algorithm that, given such a matrix A, can find a collision, can find a vector Z which is short and such that AZ is equal to 0. For example, a 0, 1 vector or a 0, 1 minus 1 vector. Assume you can find collisions to this function, and with probability epsilon. Now the probability is, the lattice lambda is fixed. The probability is over our choice of V and R. So even if we fail, we can repeat the process again using different V and R. So the fact that we solve it only with small probability is not a concern. We can boost the success probability. So assume that, yes, the cryptanalysis work and we find a collision. We find such a vector Z. Now you can expand A as the sum of V plus R. And by rearranging the terms, since this sum is equal to 0, you get that the sum of the VI's with coefficient Z is equal to the sum of the Ri's with coefficients minus Z. And notice, the vector here on the left is a lattice vector because it is an integer combination of lattice vectors, while the vector on the right is a short vector because it is a small combination of short noise vectors, Ri. And since they are equal, we found a vector which is a short lattice vector. One also needs to argue that this vector is non-zero, which can be done. And but this is the idea underlying the proof, and why breaking this function allows to solve lattice problems in arbitrary lattices. So, okay. Yes, but then the same way as you show that this vector is non-zero, you can show that it's kind of random. So if you repeat it many times, you find n you will end up finding n linearly independent vectors. But to address your question, what is more relevant is that we found vectors of a length which is related to lambda n. So even if you find only one of them, it could be much longer than lambda 1. So because we need to use a noise R which is at least as big as lambda n in order to get this uniformity. So we'll be able to find short vectors, but within a radius related to lambda n rather than lambda 1. So we are, yeah. If you take lambda n, I think it can still be, yeah, far from uniform. But if you take it a little bit bigger by a factor log n, then yes, it gets. So the smoothing parameter. So smoothing parameter basically by definition is how big of a noise you need to add in order to get something that is statistically close to uniform. And you can prove using Gaussian Fourier techniques that this parameter is bounded by this factor related to lambda n. Yeah, by something that you can make it exponentially small. So even if your algorithm works with probability epsilon, then if the statistical distance between uniform and not, and how it is related to the original lattice, the statistical deviation is smaller than epsilon, so your algorithm will still work. So yes, to be exact, yeah, there is still some dependency. It's not that the lattice is going away completely, but it's going away almost completely. And you can make it by choosing larger factor. You can make it as close as you want. Okay, so there are some shortcomings in this function of itai. One is that, well, as I explained before, you need m to be large enough so there is a collision, is a compressing function. So that's enough for some applications, including digital signatures, but we don't know how to build the public key encryption from it. And the other issue is efficiency. So this matrix is a two-dimensional object. It's a n by n matrix. So it takes a lot of space. It's polynomial sized, but is not particularly efficient. It takes a lot of space to store and a lot of time to compute. And around at the same time as itai's first discovery, there were two cryptosystems that were proposed. Trying to achieve public key encryption. One was a theoretical proposal of itai and work that had some sort of average case, worst case connection too, but based on a less standard lattice problem called the unique shortest vector problem, which is finding short vectors for certain special lattices where the shortest vector is unique in some sense. And that was primarily a theoretical proposal. At the same time, also the NTRU crypto system was proposed. It was eminently practical. It was something that you could use it in practice, but it was not theoretically as well understood as these other results. And much of the research in lattice cryptography after this first discovery of itai was aimed at improving the efficiency of lattice cryptography, addressing this point, or finding more applications, try to expand what can be done using lattices beyond just one-way function. And part of it, you can also think of it as bridging the gap between this practical NTRU crypto system and itai's theoretical one-way function. Now, I'm still, only 1/3 through the talk, and I would like to talk about the open problems. So let me just skim through. Yeah. I saw there is half an hour break. Okay, fine. So, okay, so I'll. Okay. I thought you were saying I'm not going to stay till the end if you keep talking. Okay, no, you're okay. That's okay. I'll take my time. Okay, so fine. So I'll there is a security proof showing that if you can break the crypto system, the public key encryption, then you can solve the shortest vector problem, but in the worst case, but only for lattices for which there is a big gap between lambda 1 and lambda 2. So yeah, so they had a security proof, but was based on this special class of lattices. So it was not solving the shortest vector problem in the worst case over any lattice. It was only lattice with this special structure. And the idea is that they were using this unique vector of length lambda 1 to plant a trapdoor in the lattice, which is used for decryption. No, it's not known to be NP-hard. Now, talking about NP-hardness, even SVP, CVP, or SIVP, when you take the approximate version of the problem for large enough approximation factors, say factor n, then none of them is known to be NP-hard. Only in the exact version or for small approximation factors, we know that some of these problems are NP-hard. So that objection, if you want, would apply to anything, but no, for the unique shortest vector problem, yeah, there is no NP-hardness result even for small constant approximation factors. Okay, but the main drawback of high-tide work crypto system was also practicality. It was no way, even if it was using a much stronger assumption, it was no way close to the efficiency of NTRU. So in practice, if you wanted to use, if you wanted to, you know, compromise on the security proof to get efficiency and get something usable, I mean, NTRU has been basically the target choice since then. Until this other problem came up, Oded Regev here proposed this problem called the learning with error problem. Learning with errors, which is defined similarly to High-Tide's function. And so the definition of the problem is you're given a random matrix A modulo Q, then you multiply A by some random vector S. So you can think of it as picking a random vector in the lattice generated by A, and then you add some noise to it. And so what it proved is that if you can invert this function, then again, you can solve SIVP in the worst case within some polynomial approximation factor, which again is around n. But the difference is that what that proved is that you can, in this case, you can solve SIVP using quantum computers. So you need a stronger assumption, which is this problem is hard even for quantum algorithms. And there are some classical versions of this result that were discovered later, which I'm going to mention in a few slides. So, okay, so we have a cryptographic function on one side. So this is similar to High-Tide. So it's a slightly different function. And so assume that you can break the cryptographic function on the average with small probability epsilon. So what happens? So what in the case of High-Tide was, oh, if you can do that, then you can solve lattice problems in the worst case on n-dimensional lattices within a factor n using classical algorithms. While this time for LWE, Oded's proof is that if you can break that, then the bad thing that happens is that you can solve SIVP using quantum algorithms. So that even if your attack is classical, the proof introduces quantum computing techniques. So the SIVP algorithm that you get in the end is a quantum one. Okay. Now it is interesting to compare these two problems, and even if, I mean, there are some syntactic similarities, but even more clarifying is the mathematical similarities between the two problems. If you think of it as so here you're taking a error vector E, a short noise vector, and then you add to it a random lattice vector. So computationally this is equivalent to taking a vector E and reducing it modulo the lattice. So when you add a random lattice vector, you are picking a random representative from the coset of E modulo the lattice. So think of it as reducing modulo the lattice, and that's also the operation performed by itie. So itie, when you take a product A times X, so you are reducing X modulo the kernel of A. So in a sense, they are the same function, but for different sides of the input. So in both cases, you can describe the function as, so the function is parameterized by a lattice, L. The input to the function is a short vector x, and the function is x modulo the lattice. Geometrically, you can think of taking your small error, which is in a sphere, then you cut your plane or n-dimensional space with your n-dimensional scissors, and then you divide it into parallelograms or parallelepipeds, and then you stack them together. So you just look at the displacement of the error vector within the corresponding parallelepiped. So, and this is the result. So you are mapping this sphere to a point in Rn modulo the lattice. So, so this is essentially the most basic lattice cryptographic function, and both the SIS, short integer solution problem, and the learning with errors, LWE problem, can be described in these terms. And the difference is how big of an input you start from. So when the input, this bound beta on the length of the input is smaller than lambda 1/2, then this function is injective. So all these spheres around lattice points do not intersect, and you get a one-to-one function. And when the bound goes beyond lambda/2, then the spheres start intersecting, and the function is not injective anymore. But it's not surjective yet. And when it gets bigger, then when the bound becomes at least as big as the covering radius of the lattice, then you get a surjective function. And if the radius is even bigger, then you will get a function that is not only surjective, is almost regular. It maps an input to an almost uniformly distributed output. So not only it is surjective, every point in the range is hit with roughly the same probability. Which parameter? This mu is the covering radius. And if you have a full dimensional lattice, it always exists. Covering radius is the smallest mu for which the function is surjective. I mean, so it's the smallest radius such that if you of the lattice. Yeah, the covering radius of the lattice, which is the radius of the smallest sphere, such that if you put such a sphere around every lattice point, you are covering the entire space. Alternatively, you can define it as the largest distance from any target point in space and the lattice. So itie considered this function for this range of parameters when the function is surjective, and in fact it is almost uniform. It has almost uniform output, and he proved that if you can invert this function for this range of parameters, then you can solve SIVP using classical algorithms. While Oded proved that yeah, this is very much larger, but this very much larger is just a logarithmic factor as a square root of n factor. Doesn't have to be something, yeah. It's more than a constant. So yeah, it's more than a constant. So what is needed here, but it's so the LLL algorithm approximates lattice points within factors which are exponential in the dimension. While the factor that is needed here is no bigger than a polynomial in the dimension. Actually, mathematicians, they typically study lattices for fixed dimension n, so for every fixed dimension it is a constant. But yeah, so and the dependency on the dimension is yeah. Okay, anyway, is it clear? Yeah, okay, did I address the question? Okay. Good, so the question is, So injective functions can be much more useful than these surjective functions. So you can think of it, I mean, it's not a formal argument, but think of encryption. Oh, you want to be able to decrypt, so your function has to be injective. So this is not entirely true, but to some extent it explains why using this function for small beta can be used, we know how to use it to build public key encryption, while if you use a larger beta, then we don't know how to build a public key encryption from this kind of function. And the question is, so are they hard to invert? And the answer is yes. So this one I-type proved that for this range of parameters, it is as hard as IVP, and Oded proved that also in the injective setting, the function is hard to invert, assuming some quantum hardness of SIVP. Now, you can describe the inversion problem, again, geometrically, as special versions of the closest vector problem. Now, in the closest vector problem, you are given a point in space, and you want to find the lattice point closest to it. Now, the two inversion problems corresponding to small beta or large beta are two problems that, I mean, this name is, the first one is fairly standard. It's called the bounded distance decoding problem. And it is solving CVP, the closest vector problem, within the unique decoding radius. Assume that the distance is small enough that the function is injective. So assume that your target is close to the lattice. Find the closest lattice point. While solving this problem correspond to inverting solving the LWE, learning with errors problem. So this other one, the absolute distance decoding, is assume that the distance is larger than that. It's even larger than the Covenant radius, so that no matter which target I give you, there is always a solution. But I don't ask you to find the closest one. I ask you to find any solution within this distance. So given a target point, find a point within distance Covenant radius or within some multiple, some multiplicative factor from the Covenant radius. And so we may call this the absolute distance decoding problem, so ADD and BDD. And this one is the problem corresponding to inverting I-times function. And so these two problems, the SIS short integer solution problem, I-times function, and LWE problem, can both be described as average case instances of these two problems. So we have this random class of lattices, I-times distribution, defined by a random matrix A, and then you take either the kernel of this matrix, the set of vectors, integer vectors, such that AX is equal to 0 modulo Q, or you take the span of this matrix. And now, for appropriate choice of the parameters, in fact, these are almost identical distributions. You just need to choose the codimension properly, and essentially it's the same distribution on lattices. And so inverting I-times function is solving the absolute distance decoding problem on the average for these random lattices, and the LWE problem is solving the boundary distance decoding problem for this same family of lattices. So they are average case versions of special cases of the closest vector problem. So a natural question is, how do these problems relate to SIVP, to the short integer solution independent vectors problem? And these proofs of security show that if you can break these functions, if you can solve ADD and BDD on the average, then you can solve the lattice, you can solve SIVP. Now, you can also give a reduction in the other direction. Assume you can solve SIVP. So given an arbitrary lattice, you can find n linearly independent short vectors. Now, this can be used to solve ADD. That is, given a target T, find a point not too far from it. And the way you do it is the obvious one. You find n linearly independent short vectors in the lattice, and then you round your target using those vectors. You just compute what is the parallelepiped that contains the target point. And if your vectors V1 and V2 are short, if you indeed found a solution to SIVP, this will give you a lattice point not too far from T. And for BDD, it's a little bit trickier. So how can you use n linearly independent short vectors to find the closest point to a lattice? So what you can do is to compute n linearly independent vectors, not in the lattice, but in the dual lattice, which I didn't define, but you can, so if the definition is, think of it as functions, linear functions from the lattice to the integers. And all that matters is that so it is in red, the dual lattice. So we have this set of black points, that's the original lattice. The dual lattice seems that, yeah, it's just a random set of red points I put there. Like, we don't even put them on the same line. But no, that's exactly the dual lattice. Like, these were computed, the coordinates of the red points. So what matters is that every point is... Oh, yes. Yeah, yeah. I'm not going to use the formal definition, but the formal definition of the dual lattice is the set of vectors assume that the lattice is full dimensional. So take all the vectors in Euclidean space, so not necessarily integer points, such that the scalar product between x and any point in the lattice is an integer. So it's just a standard definition of yeah, dual module for a module of a ring. In this case, the ring of Z. So what it matters is that so you can think of every dual lattice point. You can think of it as a function from the lattice to the integers, a linear function. So it can be used to partition the lattice into hyperplanes. All the lattice points that have the scalar product equal to 0, all the lattice points that have scalar product equal to 1, all the lattice points that have scalar product equal to 2, and so on. So since the scalar product is always an integer, you will only get integer points or integer values, and there are not lattice points in between these hyperplanes. So, and the longer is your dual vector vi, the smaller is the distance between these hyperplanes. We are interested in the other direction. So if you find a short vector in the dual lattice, if vi is short, then these hyperplanes will be far apart. So finding short vectors in the dual lattice allows to decompose your lattice into layers which are far apart from each other. Now, assume that you have a target T which is close to the lattice. We are trying to solve BDD, the bounded distance decoding problem, so we know that we are very close. So if you can decompose your lattice into hyperplanes, and these hyperplanes are far apart, you can easily tell on which hyperplane the closest lattice point is. Just compute the layer which is closer to the target, and you know that your solution has to be on that layer. And if you do that for n linearly independent dual lattice vectors, so you also find this other independent vector in the dual lattice, take the hyperplane orthogonal to it, take all the shifts of this hyperplane that go through lattice point, and select the hyperplane that is closest to the target. If you do this for n linearly independent hyperplanes, and then you take the intersection of all these hyperplanes, that will give you the lattice point closest to the target. Yeah. It, yeah. Yeah, there should be a basis. Yeah. You want it to be a basis, but you can turn, yeah, that's true. Okay, so yeah, but you can take your vectors and then turn it into a basis without making them much longer. Okay, so yes, this is nothing close to a real proof, but yeah, so this is a good point, yeah. So that's something to watch out for if you want to write it down as a formal proof. But what we are interested in is the bound. So how when can this be potentially used to find the lattice point closest to the target? So was it a lattice point at least in the picture, in the example? Yes. So I was lucky. Yes. So there was a basis for the dual lattice. So assume that the distance to the target is smaller than lambda 1 by a factor n, by a factor 2n. Okay? So it is some approximate version of the bounded distance decoding problem where you are very close to the lattice. Now, using transference theorems in the geometry of numbers, this can be shown to be at most 1 over lambda n of the dual lattice, and and we know that these VI's are at most of length lambda n star. So you get that as long as you are within the distance from the lattice, then this will give the correct solution, and this gives a reduction from the bounded distance decoding to this SIVP problem. So in a sense, inverting this function both in the unique decoding case and in the surjective case is equivalent to SIVP in both directions. So there are two more problems that I want to mention so that I can move into describing open problems. One of them is called the gap SVP problem, which is solving the shortest vector problem, but without finding the vector. You just want to approximate the length. You want to approximate the value lambda 1 without finding any short vector. And gap SIVP is the problem of approximating the value lambda n without actually finding short vectors. And these two problems can be related using this transference theorem in the geometry of number that says that up to a factor n, lambda 1 times lambda n star is equal to 1. It's always between 1 and n, so this product. And it's an interesting, useful exercise, if you're up for it, to show that if you can compute these values exactly, then you can find the shortest vector in the lattice. You can find n linearly independent short vectors in the lattice. And the idea is that, there are many, many different ways to do it, and yeah, I'll leave it to you to find a way to do it. However, if I only give you a way to approximate these values, lambda 1 or lambda n, then it's not clear how to find an approximately shortest vector. So relating these gap problems to the corresponding search problems are two interesting problems in the complexity of lattices that are closely related to cryptography. Let me illustrate the relation between this and cryptography. Here we have this very long list of problems and non-reductions between problems. Some of these I showed you in this talk. Now you can divide these problems, colors are not quite right. So this one, the top line is yellow, this one is orange, and this one is, I think, red, trust me. And, but yeah, the color doesn't really matter. So, so these arrows are non-reductions. So it's been shown that these problems are equivalent up to polynomial approximation factors, and they're also equivalent to the bounded distance decoding problem. So in a sense, they belong to the same complexity class. Now we have a potentially harder class that consists of SIVP and the absolute distance decoding. Again, they can be shown to be equivalent up to polynomial approximation factors, and you can reduce the problems on the first row to the problems on the second row. I mean, a trivial reduction is given by if you can find n short vectors, then you can approximate their length. So that's a trivial reduction between the problems. And then we have SVP and CVP. And again, it is possible to give a connection between the approximate version of these problems. And we know how to reduce this less trivial, how to reduce SIVP to them. Oh, this one, again, is trivial. But we don't know how to give reductions in the other direction. So open problems, so there are many open problems in this area. What makes them interesting for cryptography is that using these problems on the top, we know how to build public key encryption. Using the problems in the middle, we know how to build private key encryption or digital signatures. Or using quantum computing, quantum reduction, so we can also get public key encryption, but that requires quantum. And using the problems at the bottom, we don't know how to build any crypto at all. So try to prove more reductions between these problems are all interesting open problems, and So, for example, so if you can approximate lambda 1, can you solve SVP? If you can approximate lambda n, can you solve SIVP? And can you give a reduction from CVP or SVP to SIVP? So that's the gap between lambda 1 and lambda n. Assume that you can find vectors of length lambda n for any lattice of your choice. Can you use that by modifying the lattice to find vectors of length lambda 1, or maybe polynomial times lambda 1? And so in the exact case, it is known how to do it, but for the approximate version of the problem, so that's open. And then getting a classical reduction from SIVP to BDD would close the gap between quantum and non-quantum reductions for public key encryption. No, I didn't get to talk about, I want to skip this, it's getting too long. So there was only one slide. I didn't address the other shortcoming of iTice function, which is efficiency. So this can be addressed using algebraic lattices that have special structure. You will hear more about that in many other talks this week. And there's a connection with algebraic number theory, which is very interesting, but related to the to what I discussed earlier is this interesting point. Now, in these algebraic lattice problems, you have to choose a ring. Typically, you choose an algebraic number field, and then you take the corresponding ring of integers. And the question is, how do you choose this ring? Does the theory tell you anything about it? And by and large, the answer is no. We don't know which of these rings are good for cryptography and which of these rings are not good for cryptography. And that's really important for the efficiency of lattice-based cryptography. So the cryptographic function in the case of, is something similar to the matrix vector product, A times X, but you write, it becomes a product between the polynomials. You have a random set of randomly chosen polynomials, A1 to AK, and you multiply them by random short polynomials, say polynomials with small coefficients, and you take the product modulo something, and this polynomial here defines your ring. And the question is, what should you use as a modulus? Now, for the case of hash function, there is a very interesting observation. It's very simple, but still interesting observation of Vadim Lubashensky. I think this is not in any paper, but you can find in his PhD thesis. That is, you can build hash functions which are as hard as solving these lattice problems in any of these rings. And the trick is just compute this function, but without reduction modulo p. Now, if you find a collision, so fu equal fu prime, then fu is equal to fu prime, also modulo p. So if you can find collisions to this function, then you can find collision to this function in any of these rings. So this is as hard as solving, you can bypass the problem of the choice of the ring, just removing that in the definition of the hash function, which is still compressing. I see Leo is smiling because, as simple as it is something that can look surprising at first. And the open question is, can you do something similar for the ring LWE problem, which is the LWE version of these algebraic problems? So for each of these choices, you get a corresponding class of efficient cryptographic functions based on lattices, but how do you choose this ring? And Lubashensky, Peckert, and Regev show that when P is a cyclotomic polynomial, then you can give a connection between the hardness of inverting this function and distinguishing the output from uniform, which is essential for encryption. For encryption, you want to show that your ciphertext does not hide any partial information. It hides any partial information about your input. And so this suggests that, cyclotomic, that's a good choice for cryptography. At the same time, Christine later, she will talk about it, I think, later today or on Thursday. She will show that for other choices of rings, you can still get a function which is conceivably hard to invert, but it's easily distinguished from random. So the pitch, so it's not quite clear what to do in this case, and yeah, getting a better understanding of how the ring structure affects the hardness of the cryptographic constructions is an important open problem in the area. So I will conclude with one last slide, and then there's just the yeah, goodbye slide. So I mentioned that I was going to say more about the classical version of LWE, hardness proof. So this work of Peikert and Brakowski et al. Showing that if instead of starting from SIVP, you start from gap SVP, so which is in this potentially easier class of problems, then you can do without the classical, without quantum reductions. So you can give the classical reductions. However, this comes at a cost. One is an efficiency cost. You need either to use a very large modulus Q, exponential in the dimension, or increase the dimension to n squared. So there is a quadratic blow up in the description of your cryptographic function. And so open problems are, can you improve the efficiency of this reduction and just get a linear dependency on the size? So can you give a classical reduction starting from SIVP rather than starting from the potentially easier gap SVP problem? And that's another interesting open question. And the final one is that, so this reduction essentially applies to arbitrary lattices, but it's not clear how to adapt it to the ring algebraic setting. So there is some weak version of it that can be formulated in the ring setting, but it's not particularly interesting. Now, there are many more open problems that yeah, I could have mentioned given 5 more hours, but yeah, I asked for it, I was not given. But so there is an open problem session scheduled tonight at 7:30. This is not for me to talk, it's for everybody to bring yeah, your own open problems. So if you wanted to talk tonight, if you have any problem, yeah, please send me email at this email address, or just talk to me over lunch or over a coffee break, and I'll yeah, collect the problems, and then we'll meet tonight. Okay, thank you. If I'm happy with what? For the MP harness? Yeah, okay, so those reductions are from a worst case problem to an average case problem. There's no way to give a deterministic reduction. If you start from something which is, you know, worst case deterministic, and you want to end up with something which is random, the only way is to throw randomness in the reduction. So in this setting, random reductions is the only possibility. So in the context of proving NP harness problem, yeah, there are some open problems, yeah, in proving NP harness of the shortest vector problem under deterministic or under randomized reduction. And no, I'm not happy about randomized. I've been trying to, yeah, de-randomize, yeah, those reductions. But yeah, so that's a different setting. Here, randomness is just part of the game. I think it should be possible to bridge the gap in some sense, and though it has not been done formally. Those in the middle are the hardest instances. Now you can take, for the hash functions, you can scale the parameters down and get hardness all the way down to the point that the function is injective. And in fact, you can even go a little bit below, as long as there is 1 over polynomial probability of having a pre-image, you can still carry out the proof. So yeah, from the SIS direction, yes, you can go all the way to the middle and still prove hardness. From the LWE side, how to get up to that point is less clear. I don't know, maybe that might have something more to say about it. No. Okay. So, I mean, morally, I would say that, yeah, it should be possible to bridge it. And also, there is something interesting going on the pseudo-randomness side. So, when you are on one side of this line, the functions are, you can show that they are regular. The output is is almost statistically close to uniform. And then when you go beyond that point, it becomes computationally indistinguishable from uniform. Now, there's a little bit of a gap in this transition where, okay, the proof doesn't quite work, but my guess is that, yes, there should be some kind of smooth transition or sharp transition, I don't know, from uniform to pseudo-random. But yeah, in the context of subset sum, this problem has been studied more closely. And yes, there are reductions showing that you can go all the way to the middle and bridge completely the gap.